The objective of this training program is to provide a format of techniques, procedures, and job management for troubleshooting air-cooled and water-cooled reciprocating compressor liquid chillers. Whenever troubleshooting chillers, refer to the manufacturer's product literature for the specific unit you are working on. Combining the information provided in this program and the manufacturer's product literature will enable you to troubleshoot chillers in a confident and effective manner. This program will cover typical chiller operation, the operational check, symptoms of common problems, troubleshooting examples, and troubleshooting exercises. This program assumes you have an understanding of the basic principles of reciprocating chiller operation. The principles are basically the same for all air and water-cooled chillers. Supplemental programs listed in the appendix of the workbook will offer additional information on the operation and service of liquid chillers. In this program, we'll include a typical job visit and discuss the importance of maintaining a log. We'll also see how to use the log sheet to compare the design temperatures of the system to the actual system readings to provide troubleshooting information. Such information will show pressure and temperature trends to identify symptoms that point to chiller problems, including high and low refrigerant charge, fouled cooler or condenser tubes, proper water flow, and non-condensables. Remember, safety is the most important part of your job. Working on air conditioning, refrigeration, or heating systems means working on components that are pressurized, rotating, and either thermally or electrically hot. So be careful. Before performing mechanical service, shut off all the power. Open, lock, and tag all disconnects. Use extreme caution when troubleshooting electrically live components. Observe all safety procedures shown in printed instructions. Don't take chances. Get extra help if heavy lifting is required. All installation, modifications, and service work should conform to local and national codes. Wear safety glasses and gloves when working with refrigerants, power tools, and sheet metal. Remove watches and rings before performing electrical troubleshooting. Only qualified technicians should perform service on air conditioning equipment. Now, we'll move on to heat transfer and chiller operation. As in all reciprocating refrigeration cycles, heat is added to the refrigerant in the evaporator and the compressor. It is then removed from the refrigerant in the condenser. There is a specific relationship between the temperature of the chilled water leaving the evaporator and the saturated refrigerant temperature. Likewise, the leaving condenser water temperature and the saturated condensing temperature of the refrigerant are also related. For this program, the primary refrigerant will be HCFC-22, and the secondary will be chilled water. Understanding these primary and secondary refrigerant relationships can be very helpful in troubleshooting chillers. All temperatures in this program are stated in degrees Fahrenheit. In a typical direct expansion type water chiller, the evaporator is called the cooler, where refrigerant flows inside the tubes and water flows outside the tubes. The water gives up heat to the refrigerant, and under full load conditions, the water temperature drop through the cooler will be, depending on design, between 5 and 15 degrees Fahrenheit, with 10 degrees Fahrenheit being typical. This is also stated as the water temperature rise. It occurs in the water loop external to the cooler. Water flow rates for the cooler will generally range from 1.2 to 4.8 gallons per minute per ton. This flow rate will have been established on the basis of capacity and pressure drop when the equipment was originally selected. In order to have satisfactory temperature control, it's important that the chilled water loop is correctly sized. A good rule of thumb is that loop volume size should be not less than 3 gallons per ton of capacity for comfort cooling and 6 gallons per ton for process cooling. Refrigerant is supplied to the cooler from the thermostatic expansion valve, which is set to provide the desired superheat leaving the cooler or entering the compressor. Some superheat is necessary to prevent damage to the compressor from liquid refrigerant, but it's desirable to keep superheat as low as possible in order to get maximum cooler capacity. Traditional systems will have 8 to 12 degrees Fahrenheit superheat leaving the cooler. More recent designs with electronic controls and sensors placed directly in the compressor and cooler improve capacity by allowing lower superheat leaving the cooler. Superheat of 4 to 7 degrees Fahrenheit is typical on these newer chillers using electronic expansion valves. The heat flow in the condenser is from the hot refrigerant gas to either air flowing over the tubes in air-cooled condensers or water flowing through the tubes in water-cooled condensers. In water-cooled condensers, refrigerant enters the shell and condenses on the surface of the cold tubes. The refrigerant collects at the bottom of the condenser, then flows through the subcooler. Refrigerant then enters the liquid line with 10 to 15 degrees Fahrenheit of subcooling. This subcooling is important because it improves capacity by ensuring that the refrigerant is still 100% liquid by the time it enters the expansion valve. Any flashing of the liquid ahead of the expansion valve greatly diminishes the chiller's capacity. There should be approximately 20 degrees Fahrenheit temperature difference between the saturated condensing temperature of the refrigerant and the temperature of the entering condenser water to maintain the 10 to 15 degrees of subcooling. Water leaving the condenser will generally have a 10-degree rise over the entering water temperature. The condenser water will typically be controlled by water regulating valves if it's a once-through system. These valves are installed in the entering or leaving water line and regulate the flow of water by sensing the condenser pressure. More commonly, however, the condenser water will recirculate through a cooling tower. Here, the temperature of the water is controlled by cycling the tower fans, and the total flow at the condensers is set at a constant flow rate, typically anywhere from 1.5 to 6 gallons per minute per ton. Regardless of which system is used, water flow rates will have been established when the equipment was selected. Whenever water is involved, heat transfer surfaces tend to become fouled, and there is a correlation between fouling of waterside surfaces and the loss of heat transfer. The refrigerant saturated condensing temperature will rise as the condenser tubes become scaled. In the cooler, the saturated temperature will become lower as the cooler tubes become fouled and the heat of the secondary refrigerant, water, brine, or glycol, takes longer to reach the primary refrigerant. A scale buildup of just 1/1000th of an inch of waterside fouling can cause an efficiency drop in heat transfer between the primary and secondary refrigerant. An indication that the condenser tubes are getting fouled on a once-through system using a water-regulating valve to control condensing pressure is that over a period of time, more and more water flow will be needed to maintain design conditions. Once-through systems are more forgiving on fouling condenser tubes, while cooling tower systems are more susceptible to fouling. An indication that the tubes are getting fouled on cooling tower systems is that over a period of time, the condensing pressure will increase for the same cooling load. Proper treatment of cooling tower water is essential, but even with the best treatment, cleaning of the condenser tubes will be necessary from time to time, as with the once-through systems. A record should be maintained so that the fouling trend is charted and cleaning and water treatment can be scheduled. The logical place for this record is in the maintenance log. And of course, any other maintenance work, parts replacement, or any other work that affects system performance should be documented in the log so that the condition of the system is always known. Many chillers use air-cooled condensers with propeller fans drawing ambient air over the condenser coils. If an air-cooled condenser is used, the saturated condensing temperature at full load will typically be about 30 to 35 degrees Fahrenheit above the outdoor ambient. An increase in the condensing pressure may be an indication that the condensing coil is getting dirty. Cleaning the condensing coil from time to time, at least once a year, or more often if required, will assure optimum efficiency. The condenser fans may be cycled by head pressure controls or by air temperature controls so as to maintain sufficient head pressure to adequately feed the expansion valve when air temperatures drop below the desirable operating range. Even water-cooled condensers may require head pressure control if the condenser water drops below 70 degrees Fahrenheit. One way of keeping the head pressure up is to allow some of the water to bypass around the cooling tower, therefore reducing the heat removed at the tower. Another way is to cycle the cooling tower fans just as you would the fans on an air-cooled condenser. Using water-regulating valves is yet another way to provide the required condensing head pressure to adequately feed the expansion valve. Now let's review what we have covered so far. In this first section, we discussed safety and typical chiller operation. Now stop the tape, look at the material in your workbook, and do Quiz 1. Now that we have discussed some of the important topics of chiller operation, let's look at a typical operational check. The purpose of the operational check is to analyze the operation of a system so you can properly diagnose any problems. This should be done on a periodic basis so that abnormal trends can be spotted early and serious problems avoided. A typical operational check consists of a job site visit, an interview with the operator or owner, an observation of the equipment, a comparison of current operating data to both the design or initial data and also to the preceding sets of data, and correction of any faults or malfunctions. Before the visit, you should obtain the necessary service and maintenance literature for the unit. Wiring diagrams are essential and will normally be found on the inside of the control panel door. Contact your distributor for any necessary literature and talk to your distributor service manager if you have any questions regarding the operational check. Have the following tools available at the time of the visit: an accurate gauge manifold set, volt-ohm meter, clamp-on ammeter, digital temperature probe, the correct refrigerant for the unit, normal hand tools, flashlight, trouble light. Now we're going to go through a typical operational check using a water-cooled nominal 100-ton chiller on air conditioning duty. The chiller we selected has a microprocessor control system. Many of the readings needed for troubleshooting are provided by a digital LCD display. Many chillers are not provided with this type of electronic display. If that's the case, the information will have to be obtained from thermometers and pressure gauges at critical locations in the chiller system. When we are called on to troubleshoot a chiller, it's usually because the chiller cannot make capacity. The first thing to do is to talk to the customer or operator and review the chiller's maintenance history. You'll need information about the chiller. Start by asking pertinent questions of what happened. Learn as much as possible. Specifically, when and how the problem occurred, at what point in the operation cycle did the problem occur, under what conditions did the problem occur, and what safety controls were activated. You also need to know the history of the chiller. Was there ever a freeze-up? Any plugged tubes? Was there a motor burnout or any other damage to the chiller? Most chilled water systems are equipped with gauges and temperature measuring devices at critical points in the system. It's essential to maintain a log containing such items as the chilled water and condenser water temperatures, the condensing and evaporating saturated temperatures and pressures, and so on. Here we see a typical recommended maintenance log. A copy is in your workbook so you can study it at your leisure. This is a record of key readings and services performed on the unit. A space is provided to record the design temperatures and pressures so comparisons can be made. The maintenance log is a valuable tool because by keeping careful watch on the log, you can detect developing problems before they become critical by comparing design conditions to the actual operating conditions. You should be able to find past log sheets on the job site. If no log exists, then a log sheet should be started. When starting a new log sheet, you will need to record the design conditions of the chiller. This design information should be available either at the job site or from the manufacturer's representative, such as the local distributor or dealer's office. If you cannot get design data, then use the data taken on the initial startup of the chiller as a reference. You will also need to record the actual operating system temperatures and pressures. For example, chilled water in and out of the cooler, condenser water in and out of the condenser, chiller suction and discharge pressures and temperatures, outside air temperature, suction and liquid line temperatures, and finally, amps and volts. For chillers with 2 refrigerant circuits, a set of data should be taken for each circuit. For the purpose of keeping this program comprehensible and focused, we will treat the chiller as a single circuit machine and will only use one set of data for our troubleshooting analysis. After taking the readings, compare the current operating temperatures and pressures with the design conditions and previous operating conditions to spot any trends which might be leading to trouble. Using the log sheets will help identify refrigerant side problems, including air in the chiller, low refrigerant charge, or water side problems, including dirty or fouled tubes, low or high GPM, and incorrect gauge readings. Now let's take a closer look at the log sheet and discuss each of the entries, starting first with the cooler section. Chilled water temperature entering the cooler. Prior to startup and during initial operation, this temperature will be above the design inlet temperature. Under stabilized conditions, this temperature should drop steadily until it reaches about 54 degrees Fahrenheit. Read and record the entering water temperature to the cooler. Chilled water temperature leaving the cooler. We also need to record the chilled water temperature leaving the cooler. After the chiller is placed in operation, this temperature should be within plus or minus 1 degree Fahrenheit of the design leaving water temperature at full or part load conditions. Design leaving water temperature at full load is typically 44 degrees Fahrenheit. Under extreme light load operation, this temperature could drop below design leaving temperature. However, a control sensing the water temperature, low water temperature cutout recycle switch will shut the machine down. It's not economical or good operating practice to operate a chiller under extreme light load conditions if other means, such as outside air, will accomplish the cooling job. Chilled water delta T. Now we can determine the chilled water delta T, which is the difference between the entering and leaving chilled water temperatures. Chilled water delta T provides an indication of system capacity. If it's above or below the design delta T, then a problem may exist. More about this later. Cooler saturated refrigerant temperature. A space is provided to record the cooler saturated refrigerant temperature. Under maximum heat load conditions with the machine operating at design, this temperature should be at the design temperature. Under reduced heat load operation, when the compressor is running unloaded, this temperature will be above design. Under no circumstances, even at full load operation, should this temperature be allowed to drop below the design temperature, which is typically a few degrees above 32 degrees Fahrenheit. If the cooler saturated refrigerant temperature is at 32 degrees or lower, then the possibility of a freeze-up exists. If you cannot measure the actual cooler saturated refrigerant temperature, then the saturated temperature corresponding to the suction pressure may be used as the actual cooler refrigerant temperature. This temperature is required for determining the cooler leaving temperature difference. Suction pressure. Read and record the suction pressure. Refer this pressure reading to a refrigerant pressure temperature chart. Compare its correlating saturated temperature to the actual cooler saturated refrigerant temperature reading. These two temperature readings should be the same or at least very close to each other. Cooler leaving temperature difference, LTD. At this point, we can calculate the cooler or leaving temperature difference, LTD. This is the difference between leaving chilled water temperature and the saturated refrigerant temperature. This difference is also known as the cooler approach. Suction line temperature. This measurement is taken on the suction line near the suction service valve. Use a digital temperature probe to take this reading or read it at the control panel display if available. Record this temperature. Superheat. The superheat can now be calculated by subtracting the saturated cooler refrigerant temperature from the actual suction line temperature. On some units, the superheat may be read directly at the control panel display. Record the superheat. Chilled water flow. Space on the log sheet is provided to record the entering and leaving water pressures. The same gauge should be used to take both readings to ensure accuracy. The difference between the two readings indicates pressure drop, or delta P. It can then be compared to the design pressure drop to determine GPM. If a greater than design pressure drop is recorded, there's a possibility that the tubes are either dirty or the flow is too high. Pressure taps for taking pressure readings across the cooler should be as close to the inlet and outlet as possible and at the same height. If there's any difference in the height of the gauges, a correction will have to be made. We'll discuss this in more detail later in the program. Now let's look at the condenser section. Water temperature entering the condenser. This temperature should not exceed the design entering water temperature and on most installations should not drop below 70 degrees Fahrenheit. Entering condenser water temperature can be up to 95 degrees. However, 85 degrees is more typical. If the entering water temperature drops too low, the condenser head pressure will not be high enough to supply refrigerant through the expansion valve. Water temperature leaving the condenser. This temperature will vary with the heat load and/or tonnage. Under full heat load conditions, it should not exceed design. Under less than full heat load conditions, the temperature will be less than design. Condenser water delta T. Next, we'll find the condenser water delta T. Do this by subtracting the entering condenser water temperature from the leaving condenser water temperature. Condenser water delta T provides an indication of condenser heat rejection. Condenser pressure. Record the condenser pressure. With design water temperature and water flow through the condenser tubes and operating at full heat load conditions, this pressure should not exceed maximum design condenser pressure. When condenser pressure is higher than design, it's an indication that the chiller is operating inefficiently. Condenser saturated refrigerant temperature. On some chillers, the saturated condensing temperature may be read directly at the control panel. If this is not the case, then the saturated condensing temperature is found by using a pressure temperature chart to convert the condensing pressure to a temperature reading. This temperature is required for determining the condenser leaving temperature difference. Condenser leaving temperature difference, LTD. The condenser leaving temperature difference, or LTD, is found by subtracting the leaving condenser water temperature from the saturated condenser temperature. This also may be referred to as condenser approach. Condenser refrigerant liquid temperature. Measure the condenser refrigerant liquid temperature. If a thermometer well or control panel display is not provided to do this, strap a digital temperature probe on the bottom side of the liquid line. Subcooling. The amount of subcooling can now be found by subtracting the liquid line temperature from the condenser saturated refrigerant temperature. Condenser water flow. Space is provided on the log sheet to record the entering and leaving water pressures. The difference between the two readings, or delta P, indicates a pressure drop of the water flow through the condenser tubes. The same gauge should be used for both readings to ensure accuracy. This pressure drop can be compared to the design pressure drop to determine GPM, and if greater than design, there is the possibility that the tubes are either dirty, plugged, or the flow is too high. Pressure taps for taking pressure readings across the condenser should be as close to the inlet and outlet as possible and at the same height. If there is any difference in the height of the gauges, a correction will have to be made. We'll discuss this in more detail later in the program. Air temperature entering condenser. Measure and record the outdoor ambient air temperature entering the condenser. This is a very important factor on air-cooled condensers because it provides a reference to what the condenser saturated refrigerant temperature operating conditions should be. Air temperature leaving condenser. For air-cooled condensers, this measurement will be useful in determining temperature rise across the condenser coil. The temperature rise, or delta T, can be determined by subtracting the condenser entering air temperature from the condenser leaving air temperature. The delta T provides an indication of the heat rejection by the condenser. Line voltage. Measure the incoming supply voltage and record each leg-to-leg voltage, 3 readings. Add the readings and divide by 3 to get an average. The average should be within 10% of the chiller nameplate voltage rating. If any one line voltage reading is more than 2% from the average, then contact the electric utility for correction. This condition is called phase unbalance, and it should never be greater than 2%. Motor amperage. Using a clamp-on ammeter, record the chiller's total motor amperage. But make sure the unit has stabilized first. It should operate at least 30 minutes before taking ampere readings. Check each power lead of the chiller. Then, total and average the readings. The individual amperage readings should be within 10% of the average amperage. Also, the average amperage should not exceed the design maximum. Compressor oil level. On most semi-hermetic compressors, either a sight glass or bullseye is provided in the oil sump to determine the oil level. The oil level should be within the sight glass. However, under certain operating conditions, a fixed oil level may not be visible due to the foaming of the oil. In this section of the program, we discuss the operational check, emphasizing the importance of a log sheet and explaining the data entries. Now stop the tape, review the material in the workbook, and do quiz 2. Now that we have reviewed the data entries on the recommended maintenance log, let's discuss how to determine proper water flow and the symptoms of some common problems and how we can use the log data to analyze those problems. To determine proper water flow, you should be familiar with the manufacturer's product application data. For our example, we'll use the application data for a Carrier 30HR 100-ton chiller with 44° Fahrenheit leaving chilled water and 85° Fahrenheit entering condenser water. The manufacturer's application data will provide you with the pressure drop information needed for troubleshooting. These pressure drop GPM charts can be used to compare the actual flow to the design flow. For example, if we have a 3 psig pressure drop between the inlet and outlet of the condenser, we could verify the flow rate using the following procedure. This condenser pressure drop chart is in feet of water, so we must make a conversion. To do this, multiply the 3 psig pressure drop times the conversion factor, 2.31 feet of water per psig. Now, this equals 6.9 feet of water. If we start at 6.9 on the chart and read across to the 100-ton chiller curve and then down, we find a GPM of 225. This is the actual flow rate. To find the design GPM flow rate for this chiller, use the performance data chart in the manufacturer's application data. Starting with the 100-ton chiller with 44 degree Fahrenheit leaving chilled water and reading across to an 85 degree Fahrenheit condenser entering water, we find the design condenser flow rate to be 289.9 or 290 GPM. Now, look at the condenser pressure drop charts again. Start with 290 GPM and read up to the 100-ton chiller, then over to the pressure drop column where we find a design pressure drop of 11 feet. Remember, our sample was 6.9 feet, which reads 225 GPM. Our sample is 65 GPM short. This would be an indication of low flow in the condenser and will have to be corrected so the chiller will run at its design capacity. We will discuss this in more detail later in the program. Now, let's look at symptoms of some common problems. After a chiller has pulled the building load down to design conditions, it should keep the cooler's leaving chilled water temperature within plus or minus 1.25 degrees Fahrenheit of the design temperature. Let's say our design leaving chilled water temperature is 44 degrees, and at full load conditions, there is a 10-degree drop through the cooler. Now that means our entering chilled water will be at 54 degrees. We're using HCFC 22 refrigerant, and the suction pressure is 63 psig, which means our saturated temperature in the cooler is 36 degrees Fahrenheit. The difference between the refrigerant saturated temperature and the leaving water temperature is often referred to as leaving temperature difference, or LTD. It's an important relationship, and in a properly operating HCFC 22 system, this difference will normally be from 8 to 12 degrees Fahrenheit on older chiller systems. More recent cooler tube designs provide a much better heat transfer with LTDs being around 6 to 8 degrees. The LTD gives an indication of resistance to heat transfer. The higher the LTD, the more resistance to heat transfer. It's helpful to visualize the water temperature versus saturated refrigerant temperature in what we call an approach curve. The approach curve provides a visual indication of the resistance to heat transfer between the water and the refrigerant. As the slope of the curve decreases, it indicates additional resistance to the heat transfer. In this example, we have 54 degree Fahrenheit entering chilled water and 44 degree Fahrenheit leaving chilled water. The saturated refrigerant temperature is 36 degrees. You can see that the cooler leaving chilled water temperature is 8 degrees higher than the saturated refrigerant temperature, and the entering chilled water temperature is 18 degrees higher than the refrigerant temperature. So, our approach curve will look like this. But remember that this is for full load conditions only. At part load conditions, the 10-degree drop across the cooler will be reduced. The difference between the entering and leaving chilled water temperatures, delta T, along with the water flow rate, defines the total amount of heat transfer occurring. To refresh your memories, the system capacity in tons of refrigeration is equal to chilled water flow, GPM, times cooler delta T divided by 24. The delta T and the LTD are important and useful relationships in troubleshooting. Let's see how we can use these temperature relationships in troubleshooting some typical cooler problems. When compared to design temperature, a low delta T and a high LTD could indicate a low refrigerant charge, high water flow through the cooler, or fouled cooler tubes, while a high delta T and low LTD would indicate low water flow through the cooler. Let's look at an example where the return water is 54 degrees Fahrenheit and the leaving water temperature is 48 degrees. This gives us a delta T of 6 degrees across the cooler at full load. The cooler refrigerant pressure is 51 psig, which corresponds to a saturated cooler temperature of 27 degrees. Our LTD is now 21 degrees, a sure sign of trouble. The reduced heat transfer from the water to the refrigerant and the low refrigerant pressure indicates a low refrigerant charge. A check on the suction superheat will also likely be higher than design. Fouled cooler tubes can also cause an above normal approach curve because of the reduced heat transfer. Suppose we have a 4-degree Fahrenheit drop across the cooler with a low saturated cooler temperature of 34 degrees. The LTD is now 50 minus 34, or 16 degrees Fahrenheit. This confirms that the heat transfer has slowed. The delta T and LTD trends are the same as a low refrigerant charge, but a check on suction superheat shows that it's at or near design. In this case, the problem would likely be fouled cooler tubes. However, a refrigerant pass-to-pass leak caused by the failure of a cooler pass partition plate or gasket can give the same symptoms, usually on one circuit only. This should be checked out if the cooler tubes prove to be okay. Low cooler water flow will cause yet another set of symptoms. In this case, the water is in contact with the tubes longer and so gets colder. But because the flow is reduced, the total system heat transfer is reduced, and the expansion valve will start throttling to try to keep the leaving superheat correct. This means the refrigerant saturated cooler temperature will be lower than normal. Some typical numbers you might see in this situation are return chilled water, 54 degrees Fahrenheit. Leaving chilled water, 40 degrees. Saturated cooler temperature, 34 degrees. Here we see the trend where delta T is higher than design and LTD is lower than design. Like the cooler, similar approach curve relationships exist with a water-cooled condenser, except that the water leaves hotter than it entered, since it's absorbing heat from the refrigerant. A typical cooling tower installation would provide water to the condenser at 85 degrees Fahrenheit, and the typical 10-degree rise will give us leaving water at 95 degrees. The refrigerant saturated condensing temperature will normally run 6 to 12 degrees above the leaving water temperature, with 10 degrees being typical. So we would expect these conditions to give us about 105 degrees Fahrenheit saturated condensing temperature. And again, we need to remember that this is for full load conditions. If the LTD is high, some of the things we might suspect are fouled condenser tubes, refrigerant overcharge, low water flow, non-condensables in the system. We also need to look at the condenser delta T to help identify specifically what the problem may be. Now let's look at some problem situations. Here, the capacity of the system is somewhat low, and we only have a 5-degree Fahrenheit delta T across the condenser. Our HCFC 22 refrigerant pressure is 243 psig, which is a saturated temperature of 115 degrees Fahrenheit. This gives us an LTD of 25 degrees, which indicates that our heat transfer is being impeded. These symptoms indicate that fouled condenser tubes would be a prime suspect, especially if the subcooling is lower than design. A refrigerant overcharge causes more liquid to back up in the condenser and less tubes are available for the condensing process. With this situation, we would find the LTD and subcooling higher than design, head pressure elevated, and compressor power high with capacity somewhat reduced. We would also typically see the full 10-degree delta T across the condenser water. Low water flow would cause the delta T across the condenser to rise, and since the total heat transfer is less, the head pressure will also rise. In this example, we see a saturated condensing temperature of 115 degrees Fahrenheit, a 15-degree delta T across the condenser, and an LTD of 15 degrees. Low water flow might be caused by partial blockage of the condenser tubes. For this reason, it's good to check the water pressure drop across the condenser and compare it against the original installed values. Unlike the previous condenser problem examples, the trend of the delta T and LTD is higher than design conditions. Non-condensables are air or other unwanted vapors that do not condense in the condenser. They reduce effectiveness of the condenser and cause the head pressure to rise. The symptoms of non-condensables are similar to those of the refrigerant overcharge. You can often distinguish the two by checking the liquid subcooling, which tends to increase with the refrigerant overcharge and stay about the same with non-condensables. A comparison of the saturated liquid temperature to the condensing pressure will confirm if the condenser has non-condensables. If non-condensables are present, the saturated liquid temperature at the condensing operating pressure will not agree to the pressure-temperature relationship. With non-condensables in the system, the indicating pressure will read higher than the pressure corresponding to the actual liquid temperature. It may not be possible to obtain the saturated condenser liquid temperature when the chiller is operating. If that's the case and you want to verify the presence of non-condensables, shut the chiller down and allow sufficient time for the pressures and temperatures to equalize to ambient conditions. You can then assume the condenser saturated liquid temperature to be at ambient temperature. Use the pressure-temperature relationship previously discussed to determine whether or not non-condensables are in the system. To remove the non-condensables from the condenser, use an environmentally accepted procedure. The discussion up to this point has been directed toward reciprocating compressor chillers with water-cooled condensers. The same symptoms apply to chillers with air-cooled condensers, the only difference being that instead of working with condenser water in and out temperatures, we need now to be aware of the condenser's air in and out temperatures. Typically, at design full load conditions, a 25 to 30 degree rise is expected in the air temperature across the coil. The condensing refrigerant temperature should be about 30 to 35 degrees Fahrenheit above the ambient temperature at design full load conditions. For instance, if the condenser coil is dirty and is restricting airflow, the heat transfer from the refrigerant to the air will be impeded. The symptoms will be similar to those of fouled condenser tubes in a water-cooled condenser. The symptoms for both condensing mediums, air or water, would include a decrease in delta T across the condenser, an increase in condensing pressure and saturated condensing temperature, an increase in LTD, and a decrease in subcooling. So, whether you are troubleshooting a water-cooled or an air-cooled condenser, the trends of the symptoms of each type are basically the same. A chart is provided in the back of your workbook for your reference on operating condition trends for different system problems. In this section of the program, we discuss the symptoms of common problems emphasizing the trends of the LTDs and delta T's. Now stop the tape, review the material in the workbook, and do quiz 3. Now let's see how to apply what we have learned to solve chiller problems. In solving chiller problems, the technician will need to analyze both the cooler and condenser data before a confident conclusion can be made, as is illustrated in the following examples. We'll assume for each of these examples that you have already gathered your operating data and entered it into the log. Now we'll compare the current data to the design or original startup data to try to track down the problem. In this first example, the system is low in capacity, so we'll want to look at the cooler delta T and LTD. We see that the entering chilled water is normal at 54 degrees Fahrenheit, but the leaving water is 48 degrees, giving us a cooler delta T of only 6 degrees, instead of the expected 10 degrees, and the system is not adequately carrying the load. The saturated cooler temperature is low at 32 degrees, and from the approach curve, we see that the LTD is high at 16 degrees instead of the expected 8 degrees. Now we'll look at the condenser, where water is entering at a normal 85 degrees Fahrenheit and leaving at 91 degrees, giving us a delta T of only 6 degrees instead of the expected 10 degrees. Our condenser refrigerant pressure is 190 psig, giving a saturated condensing temperature of 98 degrees instead of the expected 104 degrees. From the approach curve, we see the LTD is low at only 7 degrees Fahrenheit. There are a few more pieces of data that are pertinent. The saturated suction pressure is 58 psig, giving us a saturated cooler temperature of only 32 degrees Fahrenheit. That's 4 degrees low. And the actual suction gas temperature is 49 degrees, giving us a superheat of 17 degrees, 6 degrees higher than the normal 11 degrees. Looking at the condenser, we see the leaving liquid temperature is 98 degrees and the refrigerant is condensing at 98 degrees. So we have no subcooling at all. If we put all this together, cooler and condenser refrigerant pressures are low, superheat is high, and subcooling has been lost. We find we have the classic symptoms of low refrigerant charge. The complaint is again low capacity. Looking at the chilled water in and out, this time we have a delta T of 8 degrees Fahrenheit instead of 10 degrees. The saturated cooler temperature is running high at 38 degrees. The cooler LTD is normal at 8 degrees. The condenser water in is normal at 85 degrees Fahrenheit, but is leaving at only 93 degrees. So our delta T is low at 8 degrees. The saturated condensing temperature is 5 degrees high at 110 degrees, and the LTD is 17 degrees, which indicates that our heat transfer is being impeded. This set of conditions points to inadequate heat rejection in the condenser. If this were due to low water flow, the condenser water delta T would be high, not low. Therefore, it would appear that fouled condenser tubes are the most likely culprit. Let's take a look at a chiller with an air-cooled condenser operating in a 95 degree Fahrenheit ambient. Once again, the complaint is low system capacity. The chilled water in and out is 54 degrees and 41 degrees for a delta T of 13 degrees Fahrenheit. The saturated cooler temperature is 2 degrees low at 34 degrees, giving us an LTD of 7 degrees. The suction superheat is normal at 11 degrees. The delta T of the air across the condenser shows it's below design with a 20 degree Fahrenheit rise and the saturated condensing temperature is 125 degrees. The subcooling looks okay, so it appears that the condenser is doing its job. It's just not loaded fully. So, turning our attention back to the cooler, we've seen that the saturated suction pressure and temperature are running low, the water side delta T is running high, and the LTD has decreased. The condenser is not fully loaded, and neither apparently is the cooler. Everything points to low chilled water flow as the problem. This can be verified by obtaining the water pressure drop across the cooler and referring to the manufacturer's product data as explained earlier in the program. You should now have a good idea on how to apply the log sheet data in determining what the problem may be on a reciprocating compressor chiller. A little later in the program, you'll have an opportunity to solve two different problems on your own. But first, let's point out some general rules on heat exchangers which may help you to troubleshoot chillers. A pump should always pump toward a heat exchanger, not draw from it. By pumping toward the heat exchanger, the pump suction strainer will collect any foreign material in the system and not allow it to reach the heat exchanger. When shutting down and isolating a heat exchanger, close only one water valve, not both, to allow for expansion of the fluid. If it's necessary to close both valves, then leave a vent open. Thermometer wells for taking temperature readings across the heat exchanger should extend into the nozzle or piping at least 3/4 of the diameter of the pipe. If there are problems with the water flow, the conditions will look like this. High flow equals a low delta T and a high pressure drop. Low flow equals a high delta T and a low pressure drop. Flow problems can be caused by a worn-out pump impeller, a blocked or dirty pipe strainer, an improperly adjusted balancing valve, airlock in the piping or heat exchanger tube bundles. Pressure taps for taking pressure readings across a heat exchanger should be as close to the inlet and outlet as possible and at the same height. This may not always be the case, and if there is a difference in the height of the gauges, a correction will have to be made as outlined in the following example. Measure the entering pressure P1, 40 psi. Measure the leaving pressure P2, 34.5 psi. Now determine the pressure difference, delta P, where delta P equals P1 minus P2, or 40 psi minus 34.5 psi, which equals 5.5 psi. Next, determine the difference in height, delta H, between the gauges, where delta H equals 3 feet minus 1 foot, which equals 2 feet. A rule of thumb is to add delta H if the entering gauge is higher, or subtract delta H if the entering gauge is lower. Next, we need to convert feet to psi using the following equation, where delta H divided by 2.31 equals psi, or 2 divided by 2.31 equals 0.87 psi. 2.31 is the conversion factor to change feet of water to psi, where 2.31 feet of water equals 1 psi. Now that we know the height correction factor, we can determine the actual pressure differential with an equation expressed as actual delta P equals differential minus delta H, or delta P equals P1 minus P2 minus 0.87 psi. Remember, the rule of thumb is that we subtract delta H when the entering gauge is lower. Plugging in the numbers for this example, delta P equals 40 psi minus 34.5 psi minus 0.87 psi, which equals 4.63 psi. In this section of the program, we covered 3 troubleshooting examples, how to use log sheet data, general rules on heat exchangers, how to correct for gauge heights. Now, stop the tape, review the material in the workbook, and do Quiz 4. At this point in the program, we want to give you an opportunity to analyze a complete system and work through 2 exercises. All the information you need to solve this problem is listed on the log sheet identified as exercise number 1. The design data is in the first column, and the operating data is in the second. Compare the operating data to the design data to track down the problem. In this exercise, we are troubleshooting a chiller with a water-cooled condenser, and as usual, the complaint is low capacity. Start by checking the delta T's and the LTDs. Then, look at the saturated suction and condensing temperatures, superheat, and subcooling. Determine what conditions are normal and what are abnormal. We want you to answer 2 questions. What is wrong with the chiller? And what correction should be made? Now stop the tape and go to your workbook and do exercise number 1. When you have completed the exercise 1, restart the tape for a review. Okay, let's see how well you've done. The chilled water entering is normal, but the leaving chilled water is 2 degrees Fahrenheit high, giving us a delta T of only 8 degrees. The LTD is 6 degrees, an indication of no resistance to heat transfer. Saturated cooler refrigerant temperature is high, but superheat is normal, so the expansion device is doing its job. The condenser water in is 85 degrees Fahrenheit and is leaving at 95 degrees for a normal rise of 10 degrees. The saturated condensing temperature is 120 degrees instead of the design 105 degrees, and our LTD is high at 25 degrees, indicating resistance to heat transfer. Since both the LTD and the saturated condensing temperature are both high, it appears that the condenser is the problem. Taking a closer look at the condenser data, we will see that the subcooling has increased from 10 to 15 degrees. Also, if we look at the chiller's amperage data, we will see that it too has increased. So, if we summarize the data trends in this situation, we find the chilled water delta T and the cooler LTD are less than design conditions, indicating the cooler capacity is low with no apparent resistance to heat transfer. The condenser delta T is at or near design conditions with chiller amperage, condenser pressure, LTD, and subcooling higher than design conditions. We can therefore conclude the problem is refrigerant overcharge. To resolve the problem, some refrigerant needs to be recovered from the chiller to bring the charge back to within design parameters. When recovering the refrigerant, use EPA-approved environmentally sound procedures. Let's look at exercise 2 in your workbook. All the information you need to solve this problem is listed on the log sheet identified as exercise number 2. This is a chiller with an air-cooled condenser on air conditioning duty that's not making capacity. Use the same procedure as in our first exercise. Compare the delta T's and the LTDs, saturated temperatures, superheat, and subcooling to the design data. We want you to answer what is wrong with the chiller and what correction should be made. Now stop the tape and go to your workbook and do exercise number 2. When you have completed the exercise, restart the tape for a review. Now let's see how you've done on this exercise. The chilled water delta T is 2 degrees Fahrenheit low, confirming low system capacity. The saturated cooler temperature is 2 degrees high, and the superheat is normal. The LTD is also normal, indicating no resistance to heat transfer. Since the cooler LTD is normal, we need to look at the condenser. Looking at the condenser data, we see the condenser air temperatures are near design conditions. However, the condensing pressure and temperature, LTD and chiller amperage, are higher than design. These data trends point to the condenser as the problem, so we need to look further. One of the common causes of high condensing pressure and temperature is refrigerant overcharge. But remember that in that case, the liquid's subcooling increases. In this case, a check on subcooling shows it's at design with 12 degrees Fahrenheit. So we need to look still further. Comparing the pressure-temperature relationship, we see the condensing pressure does not correspond to the saturated liquid temperature, an indication of non-condensables in the condenser. To remove the non-condensables from the condenser, use an environmentally accepted procedure. Removing the non-condensables should quickly bring the condensing pressure down to a normal operating level. This in turn will bring all the other chiller operating data within design parameters. With the chiller capacity back to normal, the leaving chilled water temperature should drop to 44 degrees Fahrenheit, providing a 10-degree delta T for full system capacity. This will confirm the condenser was loaded with non-condensable gases, which probably entered the system during the last maintenance activity. This concludes the program on troubleshooting. Now, let's review and summarize what we have learned. Working safely is the most important part of your job. Reciprocating chillers normally use direct expansion coolers and either water-cooled or air-cooled condensers. Condenser cooling water is usually recirculated through a cooling tower. The water must be properly treated to inhibit condenser tube fouling. For proper control, the chilled water loop must contain at least 3 gallons per ton of unit capacity for comfort cooling and 6 gallons per ton for process cooling. The most important tool in troubleshooting is the maintenance log, which provides an ongoing record of system temperatures and pressures and maintenance work. When troubleshooting, approach curves are useful for showing the relationship between the circulating water and the saturated refrigerant temperatures. 2 important relationships shown on approach curves are delta T and LTD. Delta T is the temperature drop or rise of the water as it goes through the cooler or condenser and is usually about 10 degrees Fahrenheit. LTD is the difference between the leaving water temperature and the saturated refrigerant temperature in the cooler or condenser. A typical LTD is 8 to 12 degrees Fahrenheit for a cooler and 6 to 12 degrees Fahrenheit for a condenser. Newer chillers with high heat transfer efficiencies have cooler and condenser LTDs in the 6 to 8 degree Fahrenheit range. Reciprocating compressor chillers typically have 10 to 15 degree Fahrenheit subcooling leaving the condenser and 8 to 12 degrees superheat leaving the cooler. We hope this information will enable you to troubleshoot reciprocating compressor liquid chillers in an effective and confident manner. If you would like further training on this or other subjects, refer to the appendix in the workbook.